Howdy, folks. My name's Arul Verma, and today we're going to be going over part one on a two-part series on structs. So our goals for today are to talk about what a struct is, how you can define and instantiate a struct, and how you can use a struct. So let's start by talking about what is a struct. So I'm sure you guys have some inkling of this, especially if you've worked with other programming languages, but structs are custom-made data types that hold multiple values. Specifically, structs are, like if we talk about data types, we have had a lot of our basic data types and being our integers, our floats, our booleans. And then we've had our compound data types being like strings and arrays or tuples. And structs are kind of an abstraction away from all of this. They're similar to tuples in the sense that they can hold data of multiple types without an issue. But unlike tuples, you must declare the type of the data that you're storing. And a struct is very much meant to be an encapsulation of multiple data types as well. We can see that in the bottom right, where we kind of have this struct user. And an object of type struct is called an instance of this struct user. So we can have a specific user of the struct class user. They're very similar to classes in the way they behave and the way they work. They don't share variables across instances. You can declare local functions with traits, which we're not going to cover in this lecture, or with methods like impl, which we will. And you can declare them prior to the methods they're used in, much like everything in Rust. So let's talk about how we can create a struct. We have a struct here on the top, struct user with active bool, username string, email string, and sign-in count U64. And in the bottom, we can see a creation of immutable user1. And what we do is we say let mute user1 equal user, and then we use the curly braces and we fill in all of the fields that we want to specify. We can see here that we have email colon, and we give it the data that we want it to fill in. And we do that for the username, we do that for the active field and for the sign-in count. And we can also update fields using dot notation, and we're going to get into that in a sec. So to get into or change a specific value in an instance, we use dot notation, as we saw just a few seconds ago. And this allows us to essentially change or edit the instruct instance as much as we want to. But the one thing to note is that there is no private or public in a struct, and there's no selective mutability. If your struct instance is mutable, then the entire instance is mutable, and you cannot select certain values to be mutable and certain to be immutable. Structs can be returned by functions based off of the same ownership rules that we talked about earlier. But because of how structs work, you cannot have this data inside be borrowed. And what that really means, and the implications of this, is that you cannot use the ampersand string inside of a struct because ampersand implies borrowing, and the struct must own its own data for you to borrow that struct and pass it through a function. So in this case, we can see we have our user below. And we can see that email is a string with a capital S and like spelled out instead of the ampersand str. And username is also a string. And this is because the user has to own all of its data here. So here we have two instances of our implementation of a function that returns user. And there is some interesting context here that's worth talking about. So we can see in the first one, we have user declared. We give it email, username, active, true, sign-in count 1. And then this returns it. It automatically returns it. And this works because the function transfers ownership for all of this data upon the return. And because emails and username are about string, that borrowing happens without issue. And the next thing to look at is how in the second implementation, we don't say email colon email or username colon username. And the reason for that is pretty much because of this thing called field initialization. And what this is just whenever the variable and the data that you're passing gonna give, like you can see email and email share the same name. When that happens, you can just give it the name, and Rust is smart enough to realize that, oh, these two things share the same name, the variable you want to fill in and the data share the same name. So we can just merge them and we can say, okay, this is the same thing. Now, this brings up some interesting issues. Uh, if we want to create another struct of the same, another instance of the same struct, and we want to fill in data, is there a more efficient way to do it than retyping the entire struct? Like if we want to create another instance of the same struct and have it have a lot of the same data, but with like one updated field, because the first one wasn't mutable. Is there a more efficient way to do it than retyping our entire struct? Well, yes, there's something called the dot dot notation. And essentially all it is instead of retyping every single field with user one dot, we can just say dot dot user one. And Rust is smart enough to realize that this dot dot means that whatever fields have not yet been filled in this declaration will be filled in from user one. So we specify email in the beginning, and this can be anything. It doesn't have to be email, it could be username, it could be active, it could be sign-in account. And then we say dot dot user one, and everything else will be filled in from user one. And it's a very easy way of making another struct with a lot of the same data, but without having to selectively pick and choose and like do all of the data typing out. And now let's talk about making our own functions for structs. We talked about this briefly earlier, but the keyword IMPL is how we go about making a struct-owned function. And the IMPL keyword just indicates the implementation of a function for a struct, and you can have multiple IMPLs for your particular struct. So we can see an example of this below. We have struct rectangle, and we have IMPL rectangle, indicating that all of the functions underneath are implemented specifically for rectangle. And we have our function area. Now, the good thing to note about function area is that we pass in ampersand self. This is the equivalent of passing self in like Java or C++, and it's used to give ownership of your own data to this function before it's returned after the function ends. And all methods in IMPL require you to pass ampersand self irrespective of use. There is one exception. We're going to get into that in a minute, but this is useful for like if you're trying to get data inside the function or do some sort of operation, and it allows you to segment your code by passing yourself in, do that operation, and then pass yourself back out. The exception to this entire explanation about IMPL functions is associated functions. They're the only exception to not having to pass ampersand self as a parameter. And the reason for that is because typically for associated functions, ampersand self doesn't exist yet. The implication of ampersand self is an instance of this class or instance of this struct. But in an associated function, they're typically used for constructor creation. And specifically, say we wanted to create like a square of our rectangle. And instead of saying width and height are equal to the same value, we can just pass in a size in this function square, and then that will both width and height will be initialized to that size, and then a rectangle will be returned to us. So the key difference here is that in this case, the first case of area, there is an instance that we're going to pass in and pass back out. In this case, there's not yet an instance to pass in, and the instance is being created in the function. So specifically, these are used for constructors, and the way you do it is with, as I said, dot dot, while these would be with a dot notation after your instance. So it would be like, say I have an instance of type of name A, it would be A dot area, whereas this would be a rectangle colon colon square, and A equals rectangle colon colon square specifically. Now, the other thing to note is that we have the self keyword here with a capital S. This self doesn't represent an instance like this ampersand self does. So the self keyword in general means an instance, but ampersand self means I'm passing the data of an instance over through this function. Whereas this capital self means that we are creating an instance inside and passing that instance back out. And it's an important understanding to make because this self doesn't mean an instance of rectangle. It just means a rectangle, which is a weird distinction to make, but it is a distinction that is important. So another thing to note is how do we compare structs? Can I just say with this rectangle that we had earlier, is rectangle A equal to rectangle B with the double equal sign? Can I use the not equal sign? And what about comparisons for like strings and non-integer objects like booleans or characters? Does the same rules apply? So I want you to pause the video here and kind of ask yourself these questions and write down your answers, and I'll answer them in a few minutes. Cool. So hopefully now that we're back, let's get into it. So the answer is that equal equals and not equals are not, you can't use them off the rip, but you can use them specifically for your function. But the way you'd have to do it is through implementation of implicit function call. Much like copy with the equal sign, equal equals and not equals are both implicit function calls to functions called EQ and NE. And you can't just use them off the cuff because it means that the conversion isn't working initially. And the way you can create a comparison or create some sort of check for comparison is by putting hashtag derived partial EQ at the top. This is uh, the specific library that contains all of our comparison checks. And then you can say IMPL partial EQ for and then your struct name, and your functions are going to be called EQ and NE. And this allows you to do your comparison. And we can see here that we return a bool that is basically a yes or no. And Rust uses that bool to say yes or no to check if they're equivalent or not. So we can say we pass ourself, and then we pass another object of type self. So say we have like that distinction here where self is our instance and capital self is used for another instance that's not ourself. And then we do our comparison check. In this case, specifically, all that's being checked is the ISBN. And then that is the data that's returned. So thank you for watching. If you wanted to follow along with all of this, this is chapter 5 in the Rust talks. Homework 6 has been released and MP1 is due next week. So best of luck on everything, and I'll see you guys next time.